Have you ever gazed up at the night sky, filled with its countless twinkling stars, and wondered how it will all end? The story of our universe is a grand epic, but like all stories, it has a final chapter. This isn't an ending of fire and fury, but one of slow, inexorable cold. It's a fate dictated by the fundamental laws of physics, a concept known as the heat death of the universe. Based on the second law of thermodynamics, the universe is constantly moving towards a state of maximum entropy. Think of entropy as a measure of disorder or randomness. Right now, the universe is full of structure and energy differences. Stars are incredibly hot, while the space between them is freezing cold. It is this difference, this imbalance, that allows for work, for life, for everything we see and know. But over unimaginable timescales, this energy will spread out, becoming evenly distributed. The universe will reach a state of perfect equilibrium where no more work can be done. It will be a place of uniform temperature, just fractions of a degree above absolute zero. Let's embark on a journey into this far, far future, a timeline of the cosmos's ultimate fate. Our journey begins long after our own sun has fizzled out, and humanity, if it survives, has long since departed for other star systems. We start our clock 100 trillion years from now. This is the era when the last of the stars will finally die. The universe is already a much darker place than it is today. Most stars like our sun have already completed their life cycles, expanding into red giants and then collapsing into white dwarfs. The massive stars have long since gone supernova, leaving behind neutron stars or black holes. The only stars still shining are the smallest, most frugal ones, the red dwarfs. These stars sip their hydrogen fuel so slowly that they can burn for trillions of years. But even their time is limited. One by one, they will exhaust their fuel, flicker, and fade into cold, dead remnants, known as black dwarfs. With the death of the last red dwarf, the stelliferous era, the age of stars, comes to an end. The universe is now plunged into a profound and lasting darkness, populated only by the corpses of stars. White dwarfs, black dwarfs, neutron stars, and black holes. Galaxies as we know them will no longer exist in the same way. Over eons, gravitational interactions will have flung most of these stellar remnants out into the vast emptiness of intergalactic space. The remaining objects will slowly spiral inwards, eventually being consumed by the supermassive black holes lurking at the center of what were once glorious galaxies. The universe becomes a scattered graveyard of stellar ghosts. For an almost infinite amount of time, this is the state of the cosmos, a dark, cold, and lonely place. But the story isn't quite over yet. There's another even slower process at play: proton decay. According to some grand unified theories of physics, protons, the building blocks of atomic nuclei, are not truly stable. They are predicted to decay, albeit over incredibly long timescales, far longer than the current age of the universe. If protons do decay, then all the remaining matter in the universe, the black dwarfs, neutron stars, the planets, and any stray atoms will slowly dissolve. They will break down into a sea of lighter particles like photons and leptons. This process is agonizingly slow. The half-life of a proton is estimated to be at least 10 to the power of 34 years. It's a number so large it's difficult to even write down, let alone comprehend. Over these mind-boggling stretches of time, all familiar matter will simply evaporate into a thin, uniform soup of radiation and elementary particles. The universe will become even more featureless and empty. But what about the black holes? These gravitational behemoths seem eternal, swallowing everything that comes near them. Surely they will last forever. Yet, even black holes are not immune to the relentless march of time. Thanks to a phenomenon predicted by Stephen Hawking, we know that black holes can evaporate. This process is called Hawking radiation. Quantum mechanics tells us that empty space is not truly empty. It's a fizzing, bubbling brew of virtual particle-into-particle pairs that constantly pop into and out of existence. When this happens near the event horizon of a black hole, one particle might fall in while the other escapes. To an outside observer, it looks as though the black hole is emitting a faint glow of radiation. By emitting this radiation, the black hole loses mass. It's an incredibly slow process for large black holes. A supermassive black hole, with the mass of billions of suns, would take a staggering amount of time to evaporate. We're talking about timescales on the order of a Google years. That's a 1 followed by 100 zeros, number larger than the number of atoms in the known universe. As the black holes radiate, they shrink. The smaller they get, the faster they radiate, leading to a runaway process in their final moments. The last, most massive black holes in the universe will go out not with a whimper, but with a final, brilliant flash of energy, evaporating completely. With the disappearance of the last black hole, the final act of the universe begins. This is the dark era. All organized matter and structure are gone. All that remains is a vast, cold, and ever-expanding void. It is filled with a diffuse low-energy gas of photons, neutrinos, and other elementary particles all drifting aimlessly through the endless dark. Entropy has reached its maximum. Temperature is uniform everywhere, just a sliver above absolute zero. There are no hot spots, no cold spots, no gradients of any kind. Without any energy differences, no work can be done, no complexity can arise. The arrow of time itself loses its meaning, as there is no longer a clear distinction between past and future. The universe becomes a static, unchanging sea of nothingness. A silent, timeless, and final state of perfect equilibrium. This is the heat death. It's a sobering thought, a cosmic conclusion that can feel bleak and empty. The grand, beautiful, and complex universe we see today will eventually fade into a cold, dark, and simple void. But there is a strange beauty in this finality. It's a testament to the power of the laws of physics. It's governed not just the here and now, but the ultimate fate of everything, and it gives us a profound appreciation for the present moment. The universe today is young, vibrant, and filled with energy and wonder. The Stelliferous era is a fleeting, special time in the grand cosmic timeline. The fact that we are here, conscious and able to comprehend this story, is a remarkable gift. We exist in a brief, shining window of cosmic history, where stars are born, planets form, and life can emerge to ponder it all. The end may be cold and dark, but the journey to get there is filled with light and brilliance. Thank you for joining us on this journey to the end of time. If you found this exploration of our cosmic destiny as fascinating as we do, be sure to subscribe to Space Repo for more deep dives into the mysteries of the universe.